Hello and welcome to our video lesson in photogrammetric 3D documentation.
Before we start, we would like to briefly introduce ourselves and share a few words about our intention in making this video.
We three are the team of the Photogrammetry Lab at the BHT, the Berliner Hochschule für Technik, which is a University of Applied Sciences in Berlin.
My name is Monika Lehmann.
I am Marko Koch and this is Professor Breuer, the head of our lab.
For several years we are collaborating with archaeologists in different countries. During the last years, mainly in Turkey. We support our partners in the field of three-dimensional documentation and measurement of objects of various kinds and sizes. We use multi-image photogrammetry because this method has proven to be very useful in an archaeological environment and because we are also pretty familiar with it. It's also known as SFM, Structure from Motion, as an equivalent term. A long-standing partner is the University of Hamburg. Together, we have carried out summer schools for Turkish students in the last 2 years at the excavation site in Miletus. These summer schools were funded by the DAAD, the German Academic Exchange Service. Here, we have taught the theory and practice of three-dimensional photogrammetric recording of objects. And this is also where the idea of creating a video was born, in which the skills are taught that the students learn during the summer school.
This educational video is about a three-dimensional photogrammetric recording of objects in the context of archaeology or research on historical architecture. Here we are in Miletus on the Turkish Aegean coast. The remains of a Roman bath will serve as an example. However, the geometric relationships on which the recording is based are universal. Therefore, you can transmit the instruction of this video to any other objects, even if they are smaller or bigger.
The video is aimed at students of archaeology, architecture, building research, geoinformation and surveying. But it is also intended for people who already work in these fields. Anyway, if you find yourself confronted with the task of documenting objects three-dimensionally with high accuracy, this video will guide you through the first steps. It focuses on planning, preparation and executing of the image capturing. The subsequent tasks of post-processing are not covered by this video. Exploring the object. In order to provide the basis for good planning, we need information about the object. First of all, we think of the size defined by length, width and height. But the structure of the object is also important for photogrammetric image planning. Thus, we have to care for these two basic issues at first and need to find answers to the following questions. What is the size of the object and how is it structured? It is helpful to make a sketch of the object in which you can enter all the measurements and additional information. Measure the dimensions of the object, the length, width and height. In addition, you can enter special features in the sketch. Are there any arches, niches, depressions or holes which are part of the object? Are there obstacles in front of the object or in the nearer surrounding, such as trees or holes in the ground? All details need your attention. Is the object accessible from all sides? Is there any vegetation on the surface or in the nearer surrounding? Are there trees in the immediate vicinity of the object that interfere with free access to the object or which are limiting the free choice of shooting distance? Are there trees in the immediate vicinity of the object that cover the object or cast a shadow on the object? Are there trees that interfere with the use of a drone? Are there power lines or other cables that make it difficult to use a drone? How is the texture and condition of the object's surface? You should also pay attention to the course of the sun. When is which side in the shadow and when is it illuminated by the sun? All information that we have collected so far is very useful for the next step, the photogrammetric capture planning.
Theory. The most important question must be clarified at the beginning. What is the desired resolution of the model? This is one of the basic parameters for planning the shots, and other decisions depend on it. Decisions like which camera should we use, what is the resolution and size of the sensor, which lens should we choose. The questions lead us to the subject of image scale and focal length, capturing distance and pixel size. These geometric parameters depend on each other. To make a good decision, we need to understand their interrelationships. But what does resolution actually mean? When we ask about geometric resolution, we want to know the size of the smallest part that makes up the model. In other words, how small should be the triangles to model the object's surface? The deciding factor here is ultimately the resolution of the images, which means the size of the image pixel on the object, or the area of the object's surface which is covered by one pixel. Thus, an essential parameter for the entire planning is the physical size of a single pixel on the sensor. We can find this in the technical specifications of the camera. If we cannot find it there, we can also calculate it by ourselves. To do this, we need the number of pixels on the long and short sides of the sensor. We can certainly find this in the camera specifications or in the detailed information of an image. The latter are generally stored as metadata in EXIF, which means Exchangeable Image File Format. That can be accessed via the Properties menu and Details tab in the Windows Explorer. Now we need the physical dimensions of the sensor. Is it a full-frame sensor with a 36 by 24 mm, or an APS-C sensor, or an even smaller one, for example, a micro 4/3 sensor? This information can also be found in the camera specifications. In the next step, we divide the length of one side of the sensor in millimeters by the number of pixels on this side to obtain the physical size of a pixel. To check, you should carry out the calculation for both sides of the sensor, the long and the short. In most cases, pixels are square, hence the calculated value should be the same for both sides. We already got all the parameters we need to plan our shots. We can calculate the size of a pixel on the object's surface as a function of shooting distance and focal length. Shooting distance is the distance between camera and object. Focal length is a lens parameter. Or, conversely, we can tell how far away from the object we can move the camera if we do not want to exceed a certain pixel size. Let's take a look at this sketch. It shows the sensor of our camera and the lens mounted right in front of it. The sensor represents the image plane and the lens represents the center of projection. The distance between the sensor and the lens, or more precisely the distance between the image plane and the center of projection, is called focal length. We now take a single pixel on the sensor and project it onto the surface of our object, which is located at a certain distance. All imaging rays intersect in the center of projection and diverge after leaving it until they hit the object surface, where they reproduce the pixel in a certain size. This relationship can be described mathematically, accurate and simple, using the intercept theorem, also named similarity theorem or basic proportionality theorem. Let's simplify the sketch a little more. On the left-hand side, we have the image plane or the sensor with the center of projection and the focal length as a distance between. On the right-hand side, we have the object plane, which lies in front of our lens in the shooting distance. And we have the individual pixel on the sensor, which is projected onto the object's surface. This creates similar triangles whose corresponding sides have the same ratio to each other. The ratio of the shooting distance to the focal length is therefore the same as the ratio of the pixel size on the object to the physical pixel size on the sensor. And this ratio is also equal to the image scale. Sounds complicated? Take a look at the formula. Depending on which element we are looking for, we can rearrange the equation using some algebra. Let's assume that we are looking for the pixel size on the object's surface, the object's pixel size. Then the equation should read like this. The object's pixel size is obtained by dividing the shooting distance by the focal length and multiplying the result by the sensor's pixel size. Here we recommend that all variables are included in the equation with the same unit. To get the object's pixel size in millimeter, for example, you should provide the shooting distance and the focal length and also the sensor's physical pixel size in millimeters. A shooting distance of 5 meters, therefore, would be 5,000 millimeters. And a physical size on the sensor of 4 microns would be 0.004 millimeters. Let us assume that we want to know how far we can position the camera from the object to get a certain object's pixel size that is still small enough to ensure a sufficient modeling of the object's surface with good resolution. In that case, the equation would read like this. We get the distance by dividing the desired object's pixel size by the sensor's pixel size and multiplying the result by the focal length. We can proceed in the same way if we want to know the extent of the object that we can depict with one photo. It's the same principle. We simply exchange the dimensions of a pixel for the dimensions of the sensor. The geometric relationship is the same. But always remember, keep an eye on the units.
Preparing the object. When we talk about preparing the object here, we do not necessarily mean cleaning or removing vegetation. We simply assume that this has already been done. We are primarily thinking of placing control points. But what are control points and what do we need them for? We can use control points to define a reference system. This can simply be distances, a local coordinate system, for example the coordinate system of an excavation, or global UTM coordinates. Therefore, they can support the alignment of the images, give the model a uniform scale, ensure a homogeneous accuracy of the model, help with the modeling of the camera geometry, and align the model within the selected coordinate system. This allows models from several projects to be combined. Various photogrammetric software products offer templates for printing control points. Such programs normally recognize and measure the control points in all of the images automatically. It makes the work more time efficient. However, care must be taken to ensure that the marks are produced in a size that is big enough to be recognized by the software. We use typical circular markers in our project. The black circle in the center is the actual point and the surrounding ring is a binary code that encrypts the point number. We now have to pay attention to the following. First, the marker must be large enough so that the dot in the center has a diameter of at least 10 pixels in the images. To work this out, remember the theory chapter. If we know how big a pixel is in the image, we can easily work out how big 10 pixels are. If the marker is too small, it will not be recognized automatically. Second, when we cut out the markers, we must be careful not to cut through the circle, even if it is white only. The white segments are also part of the binary code. White means 1 and black means 0. Also make sure to leave a small white margin around the code to ensure that the mark is being recognized. The control point is only recognized and measured automatically if the target is large enough and completely imaged so that the point number can be read. Important note: never use 2 or more markers with the same point number. The alignment of the images will crash. Okay. Now we have to decide how many control points we want to use and where we want to place them. The minimum number, which is required to align the model to a spatial coordinate system, is 3. But this is far too few to fulfill the task we discussed earlier. Unfortunately, there are no fixed rules to determine the number of needed control points. However, you should proceed with some sense of proportion. It is not recommended to cover an object completely with control points. Try to find a good compromise. It is important that the points are evenly distributed all over the object. Think about the 5 dots on a dice. If the dice is the object, the 5 dots are evenly distributed. The larger the object, the more control points are required. It is probably made of a series of dice. You should bear in mind that some signals may fall off or might be removed by other people. If you have enough points, you may tolerate some loss. In the case of our wall here, we have distributed the control point signals in this way, at regular intervals in the upper and lower areas, as well as on the top of the wall. Before we can stick the markers to the desired location, we should try to remove any dust. They will stick better that way. We usually use double-sided adhesive tape that we attach to the back of the markers first. A good bond to the surface is achieved by pressing firmly. If necessary, the corners of the markers can be secured with strips or gaffer tape. It is important that the markers have a good grip, as they must remain attached to the object for the entire duration of the measurement and photography. Another hint: we laminate the cut-out markers so that they are protected against moisture. However, we use matte laminating films so that the surface is not shiny or reflective. This brings us to the subject of surveying. In our example, we use a total station to determine the coordinates of the control points. At the excavation of Miletus, UTM coordinates are used instead of a local coordinate system. This can be handled differently for other excavations. It is important that the control point coordinates are determined in a system that is well defined and in which the models can be processed at a constant scale. As there are already a number of fixed points nearby, we can position ourselves at any desired location with a total station. We can use reflectorless distance measurements for most point signals. This is not possible for the points on the top of the wall. Here, we use a reflector. To prevent errors and to exclude possible inaccuracies, we take measurements of each control point from 2 different viewpoints. By doing so, each measurement is checked by a second one. If the difference between the 2 measurements is below a defined threshold, we can average the 2 results. What is a good threshold? Related to the object's pixel size.
Preparing the camera. Okay, all preparations have been completed. Recording distances and pixel sizes have been calculated. Control point coordinates have been determined. So we are ready to take the photos. Before that, we just want to quickly check the settings on the camera. We recommend choosing exposure mode A, aperture priority. This gives us control over the depth of field. Choose an F number that provides sufficient depth of field. The larger the F number, the smaller the aperture, and the bigger the depth of field. It is defined by the range between far and near point in shooting direction. Having a big depth of field is good in general because everything in object space that falls into it appears sharp in the photo. But note that the smaller the aperture, the longer the exposure time, and long exposure times carry the risk of blurring the images. You may be able to increase the ISO to solve this problem. If you are not recording raw data, you must pay attention to which white balance is set. Set the focus by choosing the right shooting distance and sight the object with the camera. Now trigger the autofocus by pressing the release button halfway or simply take a photo. Then switch off the autofocus. If you maintain the distance for a bigger series of photos and the depth of field is large enough, all the images in this series should be sharp.
Taking images. Once we have decided for a certain shooting distance, we can define the configuration of the image capture process. This should be done in a way that we move around the object at an appropriate distance by taking photos of the object at small and regular intervals. In this way, we create images with a large overlap, which should guarantee that each object point is depicted in at least 3 images taken from different directions. This is of special importance because the 3D coordinate of each point is calculated from the intersection of the imaging rays. We take a series of images from different heights so that we end up with the object completely covered with images at a predetermined distance. Images from different heights additionally increase the number and angle of the imaging rays. It is essential to proceed systematically for not losing track. In our film, the students show us how to work this out. You start with the shots from a comfortable height, here at eye level. For the subsequent image, you move a good step further. This creates two images from different directions with a large overlap. For the next image, move a good step further again. Now we have an area that is already covered by 3 images. Object points within this zone can therefore already be modeled by the intersection of 3 image rays. We continue in this way until we reach the end of the object or one side of the object. Depending on how strongly the object surface is structured in depth, it may be necessary to take the shots not only perpendicular to the wall, but also slightly tilted to the left and to the right. We recommend taking such rotated shots in a separate line. This prevents 2 shots being taken from exactly the same position, which can later lead to problems when aligning the images in the modeling software. Now that all the shots from one height are completed, we can proceed with the next height. When taking pictures from knee level or ground level, it is reasonable to tilt the camera upwards. Now proceed step by step at this new height, always keeping an eye on the distance to the object to keep it constant. If it is possible to use a ladder, this offers the opportunity to take pictures from a more elevated position. Each new angle of view results in further ray sections and helps to capture hidden areas. If the floor is not even or unstable, make sure that there is a second person holding the ladder firmly. To take pictures from even higher up, we use a drone in the example of our object. As there is a different camera mounted on the drone, different parameters naturally apply to these images. Pixel size and shooting distance are also calculated in advance here. For the systematic sequence of recording, it is also advisable to proceed line by line. If the object has special features, such as arches, holes or niches, it makes sense to record them independently after the systematic images have been taken. In this case, very individual configurations must be selected in order to cover the special shapes with a sufficient number of images. Here we also have to ensure that each object detail is captured in 3 different images from different directions. For these special positions, it might be useful to use live view and the tiltable monitor of your camera. When capturing such details, it is necessary to use a different focus setting. Shorter shooting distances are usually used here. If there is need to refocus, you should be aware that you can change the geometric properties of the camera. This is not a major problem, but there are 2 things to consider. First, with a new focus setting, you need to take a large enough number of images that overlap with each other and that also have sufficient overlap with the already existing image content of the systematically captured images. Second, it makes sense to separate the series of images with different focus settings from each other in a recognizable way. Some photogrammetric software products have an option of treating such image series separately during the alignment calculation. So if we have changed the focus and want to start a new series, we take a photo of our hand or of the sky. This gives a clear signal that a new series begins with a new focus. By doing so, we save ourselves the trouble of noting the image number or whatever. You think we are lazy? Probably, but very efficient.